Welcome to AP Statistics. Today we are tackling topic 4.4, setting up a test for a population mean or population mean difference. By the end of this lesson, you will be able to identify the appropriate testing method when the population standard deviation is unknown, define your parameters and hypotheses, and justify your choice by verifying the necessary conditions. These skills are foundational for performing what we call a one-sample t-test. Whether you are looking at a single group or comparing pairs of data, the logic of the t-test is what allows us to make claims about an entire population based on a relatively small sample. Let's get started. When we want to perform a hypothesis test for a mean, the first question we must ask is, do we know the population standard deviation, sigma? In the real world, the answer is almost always no. If we don't know the population mean, which is what we are testing, it is very unlikely we would somehow know the exact spread of the entire population. When sigma is unknown, we cannot use the standard normal distribution or z-scores. Instead, we use the sample standard deviation, S, as an estimate for sigma. This leads us to the one-sample t-test for a population mean. The t-distribution is slightly different from the normal distribution. It has heavier tails to account for the extra uncertainty of estimating the standard deviation. As our sample size increases, our estimate of the standard deviation gets better, and the t-distribution begins to look exactly like the normal distribution. But for now, remember, if sigma is unknown, t is the way to go. Sometimes, we aren't just looking at one group, but rather two measurements for the same individuals, or pairs of very similar individuals. This is called a matched pairs design. In a matched pairs design, we have two dependent samples. For example, think of a before and after study, like testing a person's reaction time before and after drinking caffeine. We don't actually analyze the two groups separately. Instead, we calculate the difference for each pair. Once we have these differences, we treat them as one single sample of data. The appropriate analysis here is a one-sample t-test for the population mean difference. Even though it involves two sets of measurements, the pairing collapses the data into one list of differences, allowing us to use the same t-test machinery we use for a single mean. It's a very powerful way to control for individual variation. When we conduct a hypothesis test, we must be very specific about what we are testing. This is called defining the parameter. In AP Statistics, you must reference three things: the population parameter, the response variable, and the population in context. If we are doing a standard one-sample t-test, we use the Greek letter mu. You might write something like this: mu equals the true mean height, in inches, of all adult oak trees in Sherwood Forest. Notice the details. True mean identifies the parameter, height in inches is the response variable, and all adult oak trees in Sherwood Forest is the population in context. If we are dealing with matched pairs, we use mu sub d. Mu sub d equals the true mean difference in test scores, post-test minus pre-test, for all students in the district. When defining mu sub d, it is vital to specify the order of subtraction, like post-test minus pre-test. Without this, your positive or negative results won't have a clear meaning. Taking the time to write a thorough definition now prevents confusion when you reach your final conclusion later. Now that we know how to define our parameters, let's talk about the claims we are actually testing. These are our hypotheses: the null hypothesis, H0, and the alternative hypothesis, H sub A. The null hypothesis is the status quo, or the statement of no effect. For a one-sample t-test, the null hypothesis always uses an equal sign. Here, mu0 represents the specific numerical value we are testing against. For example, if a company claims their cereal boxes weigh 16 ounces, our null would be mu equals 16. The alternative hypothesis reflects what we are trying to find evidence for. This is where we use inequalities. 1. H sub A, mu is less than mu0, which is one-sided. 2. H sub A, mu is greater than mu0, also one-sided. And 3. H sub A, mu is not equal to mu0, which is two-sided. If we think the boxes are underfilled, we use less than. If we just want to know if the weight is different than advertised, we use not equal to. This choice is critical because it determines how we calculate our p-value later on. Remember, the null is what we assume to be true until we have strong enough evidence to pull us toward the alternative. For matched pairs, the structure of our hypotheses remains the same, but we shift our focus to the mean of the differences, denoted as mu sub d. In almost every case for a matched pairs test, the null hypothesis is that there is no difference at all between the two conditions or measurements. H0, mu sub d equals 0. This says that if you subtracted every pair in the entire population, the average result would be exactly 0. Now, the alternative hypothesis depends on what the researcher is looking for. There are 3 possibilities. A mu sub d is less than 0, A mu sub d is greater than 0, or A mu sub d is not equal to 0. Let's use an example. Suppose we are testing a new fertilizer to see if it increases plant height. We measure the same plant before and after the treatment and calculate after minus before. If the fertilizer works, the after height should be larger, so the difference should be positive. Our alternative would be mu sub d is greater than 0. If we were just testing to see if the fertilizer changed the height in any way, even if it might shrink the plant, we would use the two-sided not equal to sign. Always read the problem carefully to see which direction is being suggested. Before we can calculate a t-statistic or a p-value, we must justify that a t-test is actually appropriate. We do this by verifying 3 specific conditions. Think of these as the rules of the road for statistical inference. The first is the randomization condition. The data must be collected using a random sample or a randomized experiment. If the data isn't representative of the population, our results will be biased, and no amount of math can fix that. When writing your justification, look for phrases in the problem like, a random sample was taken, or subjects were randomly assigned to treatments. The second is the 10% condition. This applies when we are sampling without replacement from a finite population. We need this to ensure that the individual observations remain relatively independent. If we sample too large a chunk of the population, the probability of picking certain individuals changes significantly with each draw. By staying under 10%, we keep the math stable. If the problem involves a randomized experiment rather than sampling, you often don't need to check this condition. The third and often most complex condition is the sample data condition, which ensures our sampling distribution of the mean is approximately normal. We have 3 ways to satisfy this. First, if the problem explicitly states the population distribution is approximately normal, we are good to go, regardless of sample size. Second, if the population is not normal or we don't know its shape, we look at the sample size n. If n is 30 or larger, the central limit theorem kicks in. This theorem guarantees that the sampling distribution of the mean will be approximately normal, even if the original population is skewed. Third, if n is less than 30, we must look at the sample data itself. We need to check that the data is free from strong skewness and extreme outliers. In your exam, you should actually sketch a quick plot, like a dot plot or box plot, to show you've checked this. For matched pairs, these same rules apply, but you apply them to the list of differences. If you have 30 or more differences, you're safe. If not, you must check the distribution of those differences for any major red flags. Let's put everything we've learned into practice with a detailed example. Imagine a local health department wants to check if the average amount of sugar in a brand of healthy energy bars is actually higher than the 16 grams listed on the label. They take a random sample of 12 bars and measure the sugar content of each. First, we must identify the appropriate testing method and parameter. Since we are dealing with a single group and we don't know the population standard deviation for all bars ever made, we use a one-sample t-test for a population mean. Now, let's define our parameter, mu. Mu equals the true mean sugar content in grams of all energy bars of this brand. Notice I included the population parameter, the response variable sugar content, and the population in context, all energy bars of this brand. Next, we set up our hypotheses. The null is the no-change scenario, which is the label's claim. H0 is mu equals 16. The health department suspects the sugar is higher than the label says, so our alternative is one-sided. HA is mu is greater than 16. Now we have the foundation. Before we could calculate the results, we would have to check our conditions. The sample was random. 12 bars is certainly less than 10% of all bars produced. And since our sample size is small, only 12, we would need to plot these data points to ensure there is no extreme skewness or massive outliers. If the plot looks reasonably symmetric, we are ready to proceed with the test. Now, let's look at an example involving a matched pairs design. Suppose a researcher wants to know if a new study app actually improves math scores. 10 students are selected at random, they take a math quiz, use the app for a week, and then take a similar quiz of the same difficulty. These data are dependent because each student is measured twice. Therefore, we calculate the difference for each student. Let's define our difference as post-app score minus pre-app score. The differences are 4, 3, 5, -1, 5, 3, 7, -1, 8, and 5. The appropriate method is a one-sample t-test for a population mean difference. Next, we define our parameter mu sub d. It represents the true mean difference in math quiz scores, post-app minus pre-app, for all students who might use this app. Our hypotheses. The null says the app has no effect, so the mean difference is 0. The researcher believes the app improves scores, meaning the post-score should be higher than the pre-score. In our subtraction order, that would result in a positive number, so the alternative is mu sub d is greater than 0. Finally, let's verify the conditions. 1. Randomization. The problem stated students were selected at random. 2. 10% condition. 10 students is likely less than 10% of the entire population of students who could use the app. 3. Sample data. Since our sample size of differences is only 10, which is less than 30, we must check the distribution of the differences. Looking at our list, the numbers range from -1 to 8. There are no extreme outliers or heavy skewness, so the normality condition is met. Let's deepen our understanding by looking at a two-sided example. Suppose a manufacturer of light bulbs claims their bulbs last for exactly 1,200 hours. A consumer advocacy group suspects this claim is false but doesn't know if the bulbs last longer or shorter than advertised. They just want to know if the claim is inaccurate. First, we identify the method. We have one sample of 50 bulbs, and we do not know the population standard deviation sigma. Thus, we use a one-sample t-test for a population mean. Now, we define our parameter, mu. Next, we establish the hypotheses. The null hypothesis is the manufacturer's claim. The alternative hypothesis is two-sided because the advocacy group is looking for any difference, not just a specific direction. Finally, we justify the test by verifying conditions. 1. Randomization. We assume the 50 bulbs were selected randomly from the production line. 2. 10% condition. It is safe to assume the company has manufactured more than 500 bulbs, so 50 is less than 10% of the population. 3. Sample data. Here, our sample size n is 50. Since 50 is greater than or equal to 30, the central limit theorem applies. Even if the individual lifetimes of bulbs are skewed, the sampling distribution of the mean will be approximately normal. We have successfully set up the test and justified its use. One common pitfall in AP statistics is confusing a matched pairs t-test with a two-sample t-test. It is vital to distinguish between them before you start your setup. In a one-sample t-test for a mean difference, which we've been discussing, the data points are linked. For example, comparing responses from a husband and wife, twin A and twin B, or even the performance of a left hand versus a right hand on the same individual. If you have two separate groups that have no relationship to each other, for example, a random sample of 50 students from California and a separate random sample of 50 students from New York, that would require a two-sample test, which is a different topic. Always ask yourself, if I move a data point in the first group, does it force me to look at a specific data point in the second group? If the answer is yes, it's matched pairs. Once you've confirmed it's matched pairs, remember that you are reducing those two lists into one list of differences. From that moment on, you treat it exactly like a one-sample t-test. This reduction is the key to the whole process. It simplifies the problem and allows us to focus on the average change or difference within the pairs. Let's dive into another practice scenario to sharpen our skills in identifying the correct setup. Suppose a researcher is investigating whether a new tire tread design reduces braking distance. They take 8 different cars and test each car twice, once with the standard tires and once with the new tires, in a random order. The researcher finds that the average reduction in braking distance for these 8 cars is 3 feet. How do we set this up? First, identify the method. Since each car is measured twice, the samples are dependent. This is a matched pairs design. Because we do not know the population standard deviation of braking distances, we use a one-sample t-test for a population mean difference. Next, define the parameter. Let's decide on the subtraction order. Standard minus new. Mu sub d is the true mean difference in braking distance for all cars of these models. Now for the hypotheses. The null says the new tires don't change anything. The researcher believes the new design reduces braking distance. If the new distance is smaller, then standard minus new should be a positive number. So our alternative hypothesis is mu sub d is greater than 0. Finally, the conditions. 1. Randomization. The cars should be a random sample, and the order of the tires was randomized for each car. 2. 10%. 8 cars is definitely less than 10% of all cars. 3. Sample data. Here, n is only 8. 8 is much less than 30. To justify this test, the researcher must look at the 8 differences. If there is a huge outlier, we couldn't proceed. But if the differences are reasonably clustered, the condition is met. Let's try one more example to ensure we can handle different contexts. Imagine a city planner who wants to see if a new traffic light synchronization system has changed the average commute time on Main Street. Historically, the mean commute time was 24 minutes. They collect a random sample of 40 commute times under the new system. First, we identify the method. We are looking at a single group commutes under the new system and comparing them to a historical value. Since we don't know the population standard deviation for all possible commutes under the new system, we use a one-sample t-test for a population mean. Now, we define the parameter mu. Mu is the true mean commute time in minutes on Main Street under the new synchronization system. Notice the context. We specify under the new system, because that is the population we are drawing from now. Next, we establish the hypotheses. The city planner wants to know if the time has changed, which implies a two-sided test, although they likely hope it has decreased. If the planner specifically wanted to prove the system reduced commute time, the alternative would be mu is less than 24. Finally, we justify by verifying conditions. 1. Randomization. The problem states a random sample of 40 commute times was collected. 2. 10% condition. 40 commutes is certainly less than 10% of all commutes that happen on a major street over time. 3. Sample data. Since our sample size n is 40, and 40 is greater than or equal to 30, the central limit theorem tells us the sampling distribution of the mean will be approximately normal. We don't need to see a plot of the data to proceed. To ensure you are fully prepared for the AP exam, let's recap the critical components of setting up these tests and look at a few common, tricky scenarios regarding conditions. First, choosing the test. Ask, is it one group or a paired group? Is sigma unknown? If it's one group or differences from pairs and sigma is unknown, it's a t-test. Second, the hypotheses. Always use population parameters like mu or mu sub d. Never sample statistics like x bar. The null is always equality. The alternative is the direction of the suspicion. Students often make the mistake of using x bar in hypotheses. Remember, we are testing the population, not the sample. So, always stick to population parameters. Third, the normality condition. Students often forget to check the sample size properly. Remember the magic 30. If your sample size is 30 or more, you don't need to worry about the shape of the population. But if it's less than 30, you must mention that you are looking for no strong skewness or outliers. Here is the normality hierarchy. First, check if the population is normal. If not, check if n is at least 30. If neither, check the sample data plot. In a matched pairs context, remember that n refers to the number of pairs, not the total number of measurements. If you test 15 people twice, your n is 15, not 30. This means you would need to check the plot of the 15 differences for normality. By following these structured steps, method, parameter, hypotheses, and conditions, you provide a rigorous justification for your statistical inference. This structure is exactly what AP graders are looking for. As we wrap up, let's look at one final, comprehensive example that pulls everything together. Suppose a biologist is studying the effect of a specific nutrient on the growth of a rare species of orchid. They have 40 orchids available. They randomly assign 20 orchids to a nutrient group and 20 to a control group. Wait, is this a matched pairs design? In this case, the answer is no. These are two independent groups of different plants. This would actually be a two-sample t-test, which we cover in a later topic. But what if the biologist used a different design? What if they took 20 orchids, measured their growth rate for 1 month, then applied the nutrient and measured the growth rate of those same 20 orchids for a second month? Now, this is a matched pairs design because we have 2 measurements for every individual plant. Let's set this up. The method we use is a one-sample t-test for a population mean difference. The parameter mu sub d is the true mean difference in growth rate after minus before for all orchids of this species. For our hypotheses, The null hypothesis is mu sub d equals 0, meaning the nutrient has no effect. The alternative hypothesis is mu sub d is greater than 0, meaning the nutrient increases growth. Now let's check our conditions. First, randomization. We assume these 20 orchids are a random sample. Second, the 10% condition, 20 is less than 10% of all rare orchids. And finally, sample data, n is 20, which is less than 30. We must check the sample of 20 differences for strong skewness or outliers. By carefully distinguishing between independent groups and paired measurements, and by following our 4-step setup, you are now fully equipped to tackle topic 4.4. To summarize, use t-tests when sigma is unknown. Define parameters with context. Set null to equal and alternative to the claim. And always verify random, 10%, and normality conditions. Great job today! You've mastered the setup for one of the most common and useful tools in statistics. Keep practicing these setups, and the calculations that follow will feel much more intuitive. See you next time!